Hello from the Forcetronics YouTube channel, and welcome to speeding up the ADC on the Arduino SAMD21 boards. And this includes things like the Arduino Zero, the Arduino M0, the Maker series. So it's the microcontroller on a lot of the new Arduino boards. And this is part 2. So if you haven't seen part 1, please do that first. In part 2, we're going to talk about memory concerns. We're going to do an FFT, so we're going to do some fun things like that in this video. Before I get started though, I'll mention my friends at PCBWay. They're having a great contest. I have the link right here, and I'll have the link in the description section of the video. But it's a maker contest, so where you can enter your project and win something. So check this link out. I think you have till December of 2018 to enter, so plenty of time to enter. And you guys heard me talk about PCBWay before in the past. I use their boards. I get my boards made by PCBWay, I should say. So they're a great company. And as always, check out Forcetronics.com for the Forcetronics design services, as well as we have some cheap Arduino products. And they're authentic Arduino products also. All right, let's get started. All right, here is the slide that I showed in part 1. So I'm not going to run through everything. A lot of this is what we covered in part 1. But what we're going to cover in part 2 is we're going to talk a little bit about the memory limitations. So this microcontroller has a great fast sampling ADC, but there's limitations in memory that limit what we can do with it. And then also we're going to talk about fast Fourier transforms. Looking at our signal, our captured ADC signal in the frequency domain, we're going to use Adafruit's FFT library. If you're not familiar with what an FFT is, I will give you a brief introduction, but I'll encourage you to check it out more on your own, and I'll provide a link where you can find some more information. Okay, let's talk a little bit about the memory concerns, more importantly RAM. So in the microcontroller, when our program's running, RAM is what's being used to store variables, local variables, add them to the stack, pop them off the stack. So RAM is basically our working space for memory. It also has flash memory that we can access, and you could always store stuff in, an SD card or something like that, but then there's timing you have to worry about. So let's take a simple example. So in my example, I just did a 8-bit ADC reading, right? And this chip can go as high as 12 bits. You could do 10 bits. I did 8 bits. And of course, the lower the bits, the faster you can sample, because you're not sampling as much data. I should say as much resolution for a reading. So let me take an example. So if we consider 8 bits, that's a byte, right? There's 8 bits in a byte. A byte uses 8 digital or binary memory areas in RAM. So basically an 8-bit reading can be stored in a byte, right? And we could have an array of bytes. And as I mentioned before, RAM, we can't use all of RAM for our ADC data because we use it for other stuff. Depending how big your program is or your sketch is, depends on how much free RAM you have. But let's just say we can take 20,000 bytes of this 30K byte RAM. So we can store 20,000 readings, right? And this would be a huge array. We'd be making each reading, pushing it into the array, making the next one, so on and so forth. Well, let's say we wanted to sample at 100 kilosamples per second. We could go up to 350 as we discussed in part 1, but let's just say 100. If we sample at 100 kilosamples per second and we can do up to 20,000 readings, that means we can capture 200 milliseconds worth of data, right? So that's not too much. Can't even capture 1 second of data at 100 kilosamples per second. If we upped the resolution of the ADC to 10 or 12 bits, now we need a bigger variable. We can't just use a byte. We're going to have to use a 16-bit int to store this in. Now, all of a sudden, we cut the amount of readings we can do in half because now we're taking up double the amount of memory. So now we can do 10,000 readings. If we were sampling at 100,000 samples per second, then we can only do 100 milliseconds worth of data. Now, if we double the ADC sample rate, we're going to cut down the amount of time we can sample over. So now we'd be down to 50 milliseconds if we're sampling at 10 or 12 bits. So you can kind of just see how playing around with the memory and the amount of readings you can do determines how much time you can sample. The faster you want to go, the less time you can sample. I think that's obvious. Now, as I mentioned, we could write the data somewhere else. So the SAMD21 has its own flash memory. It has direct memory access. We could use that to put the readings there, gaining us some more memory to store the readings. But remember, flash has a limited write cycle, so you can only write to flash so many times. And the flash on the SAMD21 is only about 200 kilobytes more of data or area. And of course, your program has to be stored in flash as well. So you're getting some more memory space if you use flash, but you're not getting a ton more. Now we could use an SD card that could be 32 gig or something like that. All of a sudden we have a ton of memory now, but we have to write to that SD card using SPI. So we have to make sure that our sample rate is lower than the time it takes to write to the SD card, or else we'll run out of space in RAM trying to write all of our readings to the SD card. And as an example, if you use the Arduino SD library, the high level one, I mean, it takes, I think, a couple milliseconds to write one sample of data to the SD card. So I think there's ways to speed it up if you go to the lower level libraries, but still, the whole point is you're gonna have to throttle your sample rate if you're writing to an outside memory device. So once again, this chip is great because of its ADC sample rate and its resolution, but we just have to be aware of the memory limitations. Okay, let's talk about an FFT, or a fast Fourier transform. So this basically allows us to look at a signal in the frequency domain. If you have an oscilloscope, the oscilloscope allows you to look at the signal in the time domain, and that's how we're most familiar with doing it. And I love this visual. I got it from the Wikipedia FFT site, which if you want to learn more about FFTs, I encourage you to check out that page. It's pretty good. You know, I love this picture because basically looking here, we see our time domain signal. And we can see what the amplitude of the signal is. We can, do timing measurements, but just looking at the signal, it's hard to tell what frequency components make it up. And so in this example, any signal, signal theory tells us that any signal can be made up by a sum of sine waves. And sometimes it could be an infinite sum of sine waves. But in this case, there's 3 different sine waves at different frequencies, possibly different amplitudes, that are making up this signal. And once again, it's hard to see that in the time domain. But if we go to the frequency domain over here, we can see that. The x-axis is frequency, and then amplitude on the y-axis. And so what we're looking at is where in the frequency domain do we have a signal element. And we can see the 3 places that we have frequency, and we can know that those signals are what's making this signal look like it does. Okay, I hope that makes sense. And FFTs are used in a lot of different applications for vibration analysis, for audio, and then in higher frequencies for microwave, signals and things like that. Now, the rate of our ADC sample rate could be possibly useful in vibration or audio applications. And the whole idea here is you want to make sure your signal, often in audio, for instance, you want to make sure you have a very clean signal. So looking at your signal in the frequency domain tells you, are your filters working? Are you getting the frequency components out of there that you want and leaving the ones that you want in there? Also, if you have a very sensitive signal and you notice noise on it, FFTs are great for knowing the source of the noise, because if I know where the frequency range of the noise is, I might know where it's coming from. So for instance, I may have a switching power supply in my design and it's switching at a certain rate. If I see a noise content at that exact frequency that the switching power supply is switching at, I know it's my switching power supply contributing too much noise to my signal. Oh, one last thing to mention is, I was just talking about memory concerns. Well, guess what? When you do an FFT calculation, it eats up even more RAM, right? An FFT calculation is typically an n log n type calculation, but typically if you want to save your time domain data, you have to create a whole new array to do the FFT calculations, which can further eat up memory. So point being is using an FFT with the time domain measurements does eat up even more RAM. Okay, with that said, let's look at an example. So in the first part 1, we just looked at capturing, I think it was a 60 kilohertz sine wave, I forget. But here we're going to look at a more complex signal to use our FFT library on. And here we go. So here's my setup on the left. I have my Arduino Zero, and once again, this code will work on, the Maker series. I know Adafruit and SparkFun have their own SAMD21 boards, so this should work on all of those platforms, anything that uses the SAMD21. I have my SD card holder connected to the board. This red and black clip are from the function generator that we're measuring the signal from. And then you can see I have actually a scope too. So we're going to see what the scope sees from the function generator and compare it to our ADC results. And right here, you're looking at a screenshot of the function generator. So instead of just doing a single sine wave like we did in the first one, I wanted to do something a little more interesting. So I took a 60 kilohertz sine wave and I summed a 40 kilohertz sine wave. So for this function generator, there's a modulation feature called sum. So I'm essentially adding these signals together. So a 40 kilohertz and a 60 kilohertz sine wave being added together. And my sum amplitude for the 40 kilohertz is only 50%. So the 40 kilohertz section or frequency component in the frequency domain should be smaller than the 60 kilohertz. And we'll see this in an example. But this is my signal that I'm outputting. This is my setup. And then here is an oscilloscope capture. And this oscilloscope that I'm using has an FFT Math function on it. So here's our signal coming out of the function generator, capturing it on the oscilloscope. And then what I do is I do the FFT Math. The center frequency is 60 kilohertz. So that's what we're seeing here. This is 60 kilohertz. And then we can guess that this one next to it is the 40 kilohertz frequency portion. So we can do an FFT just to sort of verify what we should see. Now, I will mention a couple things because this won't look exactly like the one we captured the ADC, and there's a couple of reasons for that. First of all, this is using a log scale, where I'm not going to have a log scale. And also, this has a much wider span. This oscilloscope, I think, is capturing at, it says it right there, 5 megasamples per second, and the span is 1 megahertz. So we're looking at a large span. For our ADC, we wouldn't look at this large of a span because we're sampling at a much lower rate. Okay, with that said, let's look at our sample capture on it in a CSV file. Okay, so I'm going to show the code for this example, but I'm just showing the results first. So we created that signal with our function generator. We outputted it to A0, the ADC input, and we captured it with the scope, but we're also capturing it with our ADC to compare it. So here's all of our readings. Actually, no, there's all of our readings. And here's the frequency domain readings. This is the x-axis, which is frequency. This is the y-axis, which is the, I guess we could say, amplitude. And then time domain, this is the x-axis, and this is the y-axis. As I mentioned before, the ADC can only do 0 to whatever the voltage reference is, and in this case, it's 3.3 volts. And so the function generator outputs a signal that is not negative. I added DC offset, so it's not negative. But then in the software, I subtract the offset. I hope that's not confusing. But that's why you're seeing below 0 readings with the ADC. So we can see in the time domain that our signal looks just like we saw in the scope and just what we're outputting from the function generator. It looks right. If we look at our frequency domain, we can see our 40 and 60 kilohertz frequency components, right? And since the 60 kilohertz one has a higher amplitude, it has a higher frequency domain amplitude as well. So here's 60 hertz, here's 40 kilohertz. And once again, remember on the scope, they're much closer together. Well, this span, this only goes to 100 kilohertz, is much smaller than the span on the scope, so that's why they're spread out more. So we can see our 60, we can see our 40, and it even tells us what frequency it was calculated at. Notice as we go higher in frequency, we get less, I'll say, noise, or our noise floor gets a little smaller. Notice here as we get closer to DC, we got some higher amplitude elements. This might be because I didn't subtract all the DC out perfectly, or in general, there's always some kind of DC component, but that's why you're seeing sort of a rise here at the low frequency end, but you can clearly see the 40 and 60 kilohertz FFT components. All right, well, that was easy. We sampled at 300,000 samples per second. We captured 1,024 readings. We're not showing all of them in the time domain. And then we did our FFT to look in the frequency domain using the Adafruit library. So with that said, let's look at the code. Okay, here is the code, and I'm not going to go redo all the stuff I did in part 1. So I'm really just going to show the new parts of the code that I added. So one big one is the Adafruit 0 FFT. So I'll provide a link for this in the video description, but I mean, you could just search on it too, you'll find it. The folks at Adafruit really make some great Arduino libraries. I bring in the SPI and SD because we're using an SD card. My sample rate is 300,000 readings per second. I'm sampling 1,024 readings, blah, blah, blah. I set up my ADC and I went over all these functions in part 1. And then my loop. I wait for all my 1,024 readings to be done, and I use an interrupt to capture each one. Then once that happens, this becomes true, this if statement. And so first thing I do is I remove the DC offset, which I mentioned, from my array. So ADC values is an array of the ADC measurements, the raw ADC measurements. I then create another array for my FFT. So I create another array in a local variable array. I set its size to 1024. I transfer all the time domain readings to that same array. So now I have 2 copies of my readings. And this relates to memory limitations, right? Because now all of a sudden I have 2 arrays that are the same size. Then the Adafruit library is very easy to use. So all you have to do is call this function 0FFT. You feed in your array. Now remember, arrays are essentially pointers. So we're really just passing the memory address of the array. And what I mean by that is, after this function is done, the calculated FFT values are then put into this same array. So it takes those time domain measurements, does the calculations, turns them in the frequency domain, and puts them back in the same array. I then start my SD card library. I then create a file. And then I go through this for loop to feed all my values to the file, 1 row at a time. And the new function you're seeing here is another one from the Adafruit library. It's FFT bin. This is returning the values of frequency. So remember, there's an x-axis, and the x-axis contains different frequency points. That's what's in FFT bin. All the frequency points that were used to make an FFT calculation are in this array. So we can grab them. Here's our array full of our FFT values. You can see I'm adding a comma after each because this is going into a CSV file. I then have my x-axis for my time domain, and then I have my time domain measurements from the ADC. And I just loop around till I print them all, and then I close my file and I'm done. So that was all the addition to the code for capturing or doing the FFT. And this is really a great library Adafruit made for using the FFT. Okay, that's it for part 2 in this series on speeding up the ADC on the Arduino SAMD21 boards. If you have anything to add or any comments or questions, use the comment section below the video. And I'll just remind you again, check out PCBWay and their great maker contest. Thank you for watching.